Transmission line magnetic coupling. There are two transmission lines going side by side for 10 kilometers. Left line is energized and the right line is under maintenance. It is grounded at the beginning of the segment and open circuit on the other side. The lines are made of aluminum conductors separated by 1 meter clearance. Conductors are placed 18 meters above the ground surface. And our task is to calculate the induced voltage on the open circuit of the second transmission line. Okay, let's start QuickField now. In QuickField, I create new problem. T-line. Next. Problem type is AC magnetics. Frequency is 50 Hz. The transmission line is long and in every cross section we face the same 3 conductors and the same magnetic field distribution. So I'm going to simulate only a single cross section and the model class is 2-dimensional plane parallel and I can add an electric circuit file to the project. Circuit 1. Finish. On the left you can see the problem pane and on the right is the geometry model editor window. You can draw the geometry model here or you can import the geometry model from the AutoCAD DXF file. The model is simple, so I'm going to draw it here from sketch. First I will insert a circle with a diameter of conductor 1 centimeter. Insert. Close. Zoom to fit. Now I need 2 circles more, so click here to select, right click, duplicate selection, displacement. I need 2 copies more, and the distance between the conductors is 1 meter. Okay. Again, zoom to fit. Now you see there are 3 conductors. And these conductors are placed 10 meters above the ground. Edit, move selection, displacement by 10 meters up. Okay. Now these are conductors of those transmission line. Then I duplicate these conductors, edit, duplicate selection 20 meters to the right to get the second transmission line. Okay. Now switch to insert mode and draw the Earth surface. QuickField cannot simulate magnetic field distribution in the infinitely large space, so I should limit the simulation domain. And I'm going to draw the A block boundary and I will draw the F block boundary. Okay, the geometry model is ready. Now I should assign labels. Through labels we can distinguish objects and provide material properties. Switch to select object mode, click the object to select and type in the label name. This is air, this is soil. Zoom in. These dots are in fact blocks. You can select the block by clicking it inside or you can use the rubber band. Right click and drag to draw the band, and you have selected the block. This is conductor phase A. Again, zoom in, right click. This is conductor phase B. And this is conductor phase C. This would be the energized line carrying the current. And we have the second transmission line. Right click to select the conductor. This is A second. This is B second. And this is C second. Okay. I believe that far away from the transmission line, the magnetic field fades to 0. So at this boundary, I will set 0 magnetic field condition. So far, these are just labels. Now let's provide physical properties for these labels. Double-click the label name in the tree and type in the relative magnetic permeability of the air, which is 1. Relative magnetic permeability of the soil is 1, and electrical conductivity is 0.1. The left line conductors carry the current of 200 amperes, which is Earth mean square value, and in QuickField we should specify the magnitude times square root of 2. Okay, I do not specify conductivity here because I'm not interested in the voltage drop nor in the Joule heating losses in the energized line. The line is only used to generate the magnetic field. So I do not specify conductivity here. Okay. Phase B. Same total current value, but the phase shift is 120 degrees. Okay. Phase C. Same total current value, but the phase shift is minus 120 degrees. Okay. Now for victim line, I specify permeability. Now I'm interested in voltage drop, so I'm going to specify electrical conductivity, which is 37 megasiemens per meter for aluminum. There is no voltage or current source to be specified here. The voltage will be induced by the energized line through the magnetic coupling. Okay. The same material properties I specify for the victim line conductor phase B and for the victim line conductors phase C. Okay, and as I said, far away from the transmission line, magnetic field fades to 0, and I specify 0 magnetic potential value. Okay. Now open the electric circuit. Okay. Here I drag labels with non-zero conductivity, which are victim transmission line conductors and the soil. Victim line is grounded at one end, so I will use the wire to connect these conductors to the ground. You can add the grounding resistors here. You can add the capacitors to take into account the capacitance between the transmission line and the soil. But in my case, I would like to keep the circuit simple. Now back to geometry. Before I could run the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated. Now save all problem files and solve the problem. Let's take a look at the results. Here you can see the magnetic field lines and the color map of the current density distribution in the soil and in the victim line conductors. You can adjust the field picture and switch on, for example, the color map of the magnetic flux density. Let's adjust the scale. You can use the local values tool. Click any point and get the exact value of the flux density, of the field strength, and other field parameters. You can use the contour tool. Draw the contour line, for example, here above the ground, and get the field distribution along this line on the XY plot. This is the flux density profile. And the exact values you can see in the table. And apart from the field simulation results, you can see the electric circuit simulation results. The induced voltage in the victim transmission line due to magnetic coupling is 1 millivolt per 1 meter of the conductor length. Our transmission lines go side by side for 10 kilometers. 10 kilometers. Okay. Yes, I would like to solve the problem again. Take a look at the results. Open the circuit results. And now the induced voltage is 14 volts per 10 kilometers of the transmission line length. This is for the phase A. For the phase B it is 13, and for the phase C it is again 13. These voltages are induced because of the magnetic coupling between the transmission line. The victim transmission line conductors are located in the alternating magnetic field generated by the first transmission line. And in QuickField you can visualize the alternating magnetic field. I will adjust the field picture, switch off the color map of the current density, and I will add more field lines. Okay, now I'm going to animate the picture. You see how the magnetic field of the transmission line changes in time. If you search for the transmission line magnetic coupling on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.